Again, apologies in advance. When I first sort of thought about setting up the series of lectures, I had great plans for what I was going to do in these no, in these lectures, and of course, I never got round to doing exactly what I wanted to. So these next two talks are a little bit overlapping, and they've probably got, their titles are probably a little bit misleading, and they're going to be very eclectic, basically jumping around. But again, I really what I'd like is um, uh, to get some questions. But please do ask questions though along the way, and 'cause that's really what this is about. Is not necessarily what I'm sort of talking about, but what you want to know about. So I we're going to talk about telescopes now, radio telescopes, and but to say it's going to be very sort of eclectic and jumping around all over the place. And just want to start off with a very simple radio telescope, and this is the sort of radio telescope though that I worked on when I first started, and what Sarah worked on when she first got involved in radio astronomy as well. And back then it was necessarily very analog. The digital side of things was pretty primitive, but the basics are still there. No matter how much more complex you get, there's still a radio telescope actually is a very simple thing. And it kind of annoys me when people say that you can't possibly understand a radio telescope end to end. I think you can, and now there's people in this room who do, and down to the last detail. But at the conceptual level about what actually happens along the way is no, I think is not that difficult. So in a radio telescope basically consists of two main bits. One is the receptor, which is the thing that takes the radio waves and converts them into an electrical signal. And then there's the radiometer. That's an old style term, and it says what it is. It's you're metering the radio waves. You're measuring their temperature effectively. You're measuring the power in the in the signal. I remember in the previous lecture I introduced brightness, temperature. I said that astronomers are lazy. They take anything that's got horrible units and we convert them to a temperature. And so I'll be talking about temperatures a lot of the time as well now, and you're wondering why temperature when we're talking about telescopes and electronics, but we'll see why that is. So what we really have is a thermometer. Radio telescope is a thermometer. It measures the amount of energy that's being received by the receptor. And what I've put on the slide is a simple radiometer. It's maybe got most of the bits and pieces that a radiometer would have. So you start off, you have to have an antenna because we have to have a transducer that takes our electromagnetic wave and makes it into a voltage. And I've called that a feed antenna. Now, in the case of something like SK low, the feed antenna is the actual antenna. For SK mid and for Meerkat, the feed antenna is a sub antenna within the bigger receptor. But basically, what I want there is something that takes radio waves and makes them into electric signal. One of the things I probably haven't emphasized enough is just how weak these signals are. These are very, very, very weak signals. I've been bandying around Boltzmann's constant K. It's got a minus 23 in its exponent. And it's that minus 23 which actually tells you that's the order of the power that's in these signals, of the order of 10 to the minus 23 watts or less. The unit of Jansky, the flux unit that we use, is 10 to the minus 26 watts per square meter per hertz. So these are very, very weak signals. So we have to amplify them. So we amplify them with a low noise amplifier. We then have to define the band that we're working in. We define a frequency band, and we have some sort of filter which says we're going to work from this frequency to this frequency. Excludes the other frequencies because we either can't swallow that much bandwidth. There might be RFI in other bits of that bandwidth. And so we do then have a defined frequency band. What we may or may not then do is to put this through a heterodyne system, a mixer, which takes that frequency band and shifts it to a lower frequency in general. And we can do that with impunity because of image rejection and Nyquist theorems and everything else, but it basically takes, we don't lose any information If we just shift that band down to a lower band, which I sort of try to show in the bottom graphs at the bottom there, by multiplying by a local oscillator, why do we move to the lower frequencies? Everything's much easier down there. The electronics is cheaper. The technologies are easier to deal with. We put in more amplification. We put in more filtering. And then we have a power detector. So this is the whole thing about a radiometer. We have a power detector. And as you saw in my previous slide, previous talk, if you were here, I looked at the sky intensities. Intensities are in units of power. In the end, what we do is we measure power, not voltage. And how do you get power from a voltage? Well, from school electricity or whatever, that power is proportional to voltage squared, V squared over R power. So you've got to square the voltage. Now, the way we used to do this, and quite literally used to do this, is to have an analog square law detector. And so what you do is you have a nonlinear electronic circuit, includes a diode. The diode's voltage current characteristic is exponential, but everybody knows that an exponential is something like a parabola, and the parabola is x squared. So you can use a diode to square a voltage in a simple circuit that's there, just literally that circuit, a diode, a resistor, and a capacitor. And the voltage that comes out of that simple circuit is proportional to voltage squared on the input, which means it's proportional to power. And you record that signal, and that's a radio telescope. So that is literally the radio telescope that I did my MSc and PhD on. Sarah did her master's on. And of course, now we've got more sophisticated. What we do is we digitize that signal, and we do all of that arithmetic in numerics now. And we have a digital radiometer, but the principles are all still the same. What we're doing is converting a radio signal into an electrical signal and measuring the power in that electrical signal. Now, one of the simplifications I've got here, it's a single polarization. We now record two polarizations, two separate polarizations. So there's effectively two of those in parallel. And as we get towards the DSP side, those two signals get combined with each other to do fancy things that we'll get onto. So this is something which some of you will be more familiar with, which is the Meerkat architecture, which is a pretty good representation of a modern radio telescope, particularly a mid-frequency telescope, though, which is using a reflector antenna. So we have a bunch of antennas, and on each of those antennas, we have the optics, the reflector optics. The reflector optics is all completely passive. All that's doing is effectively taking our feed that we've got there, each of those feed antennas, and making them look bigger. So as I said before, that the intrinsic size of a transducer, which takes a radio wave and converts it into an electric signal, is of the order of a quarter to a half a wavelength. And that then sort of limits the size, the collecting area of that receptor. Now, in order to take these very weak signals that we're receiving, we need to boost that signal in some way. So we have to make that dipole look bigger. And the way you make the dipole look bigger is you put it into this magnifying optics, effectively, parabolas and hyperbolas, and shape them as well. And you end up with something which is the size of the dish, which then focuses down onto the simple dipole in the end that you have to have. And these days, we digitize that signal immediately. We don't even put it through a mixer or anything. We just say, give me that signal, and I'll make it into digits. Okay, that's not going to be true for the SKA anymore, because at the higher frequencies, we are going to have a heterodyne stage, which moves things down to lower frequencies, because we realized that it was just one step of hubris too big to be able to digitize high frequency signals. Even though you can do it, the A to D converters are not that great. But basically, you digitize the signal as quickly as you can, right there up on the feed, because a digital signal doesn't rot. It's analog signals. You put them over transmission lines, and you put them through analog components. It distorts the signal in some way or another. Once you've got the signal in numbers, you can do any. You can transport those numbers without loss, and things like that. So that's a good thing. We use modern internet switches and transmission systems to move our signals around rather than coax lines like we used to. And we bang all of that then into a correlated beamformer, basically a big digital signal processing device, and we'll look into that in a little bit longer. And depending on what we want to do, that digital signal processor sort of massages that digital data in various ways. And in the case of Meerkat, we actually pass that data on to user-supplied equipment, and they're even more specialized kind of processing. But one of the things that holds all of this together is we absolutely need an accurate time and frequency reference. And so that's a very big part of a radio telescope, is the time system. And that holds the whole thing together. So the TFR system at the bottom there is really important to us. But just to go back to the history, and look at the wide range of radio telescopes or antennas that we've looked at. So Jansky, back in the day, his antenna was basically a dipole. I've forgotten the name of it. It was widely used back in the day. It was a directional antenna, but working at very low frequencies, at 20 megahertz. I think in his paper he mentions working at high frequencies. So back in the 1920s and 30s, high frequencies was 20 megahertz, and he pushed it around manually. It had wheels, and that was where we started. Reba was quite a remarkable person. Dish antennas were not a big thing, in the 1940s, and he built one in his mother's backyard, largely on a wooden frame, obviously metal reflecting surfaces, and a sort of a microwave waveguide feed. Was a jam jar with a bit of wire in it, basically, but it was it was quite a thing. And then, of course, the electronics, the amplifiers and everything that went behind it. But it was very early on that the concept of dishes came along. And he did work at higher frequencies. He was working at several hundred megahertz. Something I should have mentioned earlier. So there was this whole controversy about whether you should be able to see radio signals or not. And because people believed that the only thing that determined the spectrum of radio signals was the black body curve, it made sense to go higher in frequency in order to see things, because that would take you up the black body curve. But he actually fiddled with a couple of frequencies, and when he went up in frequency, he saw less, and then he went down in frequency and saw more, which was one of the reasons why the optical people really didn't believe him, because now he was showing that this radiation from the Milky Way was going the opposite way to the black body curve. So that was heresy, great heresy. And then a really big step where Lovell built the Mark I, which was, this was real bravery, stupidity, or whatever, but British bridge building at its best. The Mark I telescope was built out of old battleship components and built using the same technology that British Rail used to build bridges and railway stations. If you look at it, it is actually a railway station and a battleship combined. But the thing was that the electronics and everything around about then, and the sweet spot for radio astronomy was around about a gigahertz, because that was felt 900 megahertz was a good place to aim for. The wavelength then was of the precision that you need to build your optical surfaces to for any telescope is some fraction of the wavelength. So as you go up in frequency, the wavelength goes down. It means you have to build these things to higher precision as you go up in frequency. And using bridge building technology, building something that worked at 900 megahertz was reasonably easy. Reasonable, anyway. But then the prediction of the 1420 megahertz line came along, and the discovery of the 1420 megahertz line in the Netherlands changed the whole thing. And so there was just this absolute scope creep that he had to build a telescope that worked at about twice the frequency it was designed to. And the sort of empirical equations for the link, surface accuracy to cost is a horrible sort of steep curve, and he blew the budget. And so he was saved by Sputnik, because he could detect Sputnik with this thing. When he built the Mark II, he thought, okay, well, one of the cost drivers for dish telescopes is the diameter, or the height of the dish, the height of the support structure. And so why don't we build an elliptical dish, which is smaller in one dimension than the other? So you could build it squatter. It would be lower to the ground. It would be cheaper. But as we'll see, the thing with an elliptical dish is you end up with an elliptical beam, and that's just a terrible, terrible thing to deal with. And so if you look carefully at the Mark II picture, you'll see that there's a surface on top of the elliptical surface, which is actually circular. And so the actual diameter is a lot less, the effective diameter is less than it was. Going back to the Rhodes, first radio telescope in South Africa, that was a helical antenna. And that was the sort of decided on for all sorts of good reasons. One was that the signal coming from the sun, which was the target for these observations, was circularly polarized. And helical antenna is like a dipole, except it picks up circular polarization, which is great. And it happens to match quite well into the electronics of the time, and it had quite a wide bandwidth. But there was a lot of a lot of back of envelope calculations. Jocelyn Bell's telescope, as I say, was washing lines, strung up in Cambridge. But back then, you could use a washing line to make amazing discoveries and get your supervisor a Nobel Prize. The Hoghorn that discovered the cosmic microwave background went really back to first principles and said, well, let us actually just build a feed horn. Let's not put it into a reflector optics. Let's just take that and point it at the sky. And why would you do that? Because this was an experiment. This was a very specific experiment to look for a very specific signal. And you wanted an antenna which had very, very understandable analytic characteristics that you could calculate the beam pattern, as we'll see later, for this antenna very precisely, which took out all sorts of uncertainties in the measurements that you were going to do. I was talking during the lunch break of people like myself who come from a single dish background. It is way harder than interferometry. I'm not saying that it's more complicated, it's much harder. You're doing absolute measurements rather than relative measurements. Absolute measurements are very, very hard to make because any instability in your baselines or anything else masquerade as your signal. So when you're looking for an absolute signal on the sky, like the cosmic microwave background, you build something like this. So this is the distinction between experiments and facilities. The SKA is a facility. It's a facility for doing radio observations over a wide range of fields. This sort of antenna is looking for one thing only. And that was what caused quite an issue for SKA low, because the big science objective for SKA low is at the epoch of reionization, which some people say is an experiment. And there's a whole lot of EOR experiments out there which are building specialist antennas, specialist telescopes to look for that signal. But you can't sell that because that's just an experiment, and it's, by definition, it's over after a few years. So there was a big tension in the low frequencies aspect. In fact, a split where people went their own way or went with SKA low. It's another story. But anyway, so the radio astronomy is defined by big dishes. I mean, the Jodrell Bank, the Effelsberg 100-meter GBT, and of course Parkes. And these things are all subjects of films. And we've sort of spoken already about the Hart-Pierce Hook 26-meter dish, and the role that it and particularly George Nicholson have played in forming radio astronomy in South Africa. But again, just an evolution here. That dish, when it was built by NASA, was operating at 960 megahertz. It had a mesh surface. George, the NASA people, so then Deep Space Day network went up to 2.3 gigahertz, so the surface was replaced with a perforated aluminium surface. But George had greater aspirations. He said, no, we can make this thing work to higher frequencies up to 22 gigahertz and replace the whole surface with a solid surface. Could do that because these NASA dishes were built in the same kind of era as Lovell, over-engineered to the nth degree because they didn't have the fancy mechanical modeling software that you have now that you can optimize. You just went belts and braces. And so this dish, which is as old as I am, is way beyond its sell-by date, but it is operating in a mode which was never designed to do, well, in the first instance. But we don't do that anymore because we can't afford to. then there was this drive for aperture. We wanted to chase weaker and weaker signals, and so you had to build bigger and bigger telescopes. And Arecibo was really the epitome of this. And again, if you've seen James Bond in GoldenEye, you'll know this dish very well. But of course, poor old Arecibo fell down and is no longer. But fortunately, our Chinese colleagues came and built fast, which is just really an act of absolute hubris. They're just saying, we're going to do it. We're going to build this really big thing, and it's going to be really this difficult. But they did it because they had these valleys which allowed them to at least have a vague shape of a parabola before you started. This thing, if you can ever get an opportunity to visit this thing, it is absolutely worthwhile. It's probably the most impressive piece of engineering that you will ever see. It really is. You go walking around the edge of this thing, it's 500 meters across. That whole surface is deformable, so they can form a parabola, the parabolic shape over any part of it. It's absolutely amazing. And then you sort of sublime to the ridiculous. No, LOFAR in the Netherlands, again a low frequency telescope, went to simple dipoles, just bits of wire, that don't even look like antennas, and are making, amazing, discoveries. Because what they're doing is they pushed into this low frequency regime, and so that's one of the ways of discovery is to go find a niche, a sort of parameter space where nobody else is looking. So LOFAR, even though they were operating in the Netherlands with terrible RFI problems, were able to do science that nobody else had done, because they had a large aperture of low frequency antennas. Then you can go for the real experiment, and this is the reach dipole antenna just around the corner from Meerkat, an experiment between various partners, including Cambridge and Stellenbosch University, where you build an absolutely, just like the hog horn, you build an absolutely simple antenna that you can characterize very precisely theoretically. So you know its performance very precisely. You don't have to calibrate things out afterwards. You know everything before you start, so that when you go and do your measurement, there's minimal calibration. So one of the things in radio astronomy, what we like to think we're doing is we're measuring the sky with our radio telescope. What it turns out is we collect data, and then we have to apportion bits of that data to the sky and other bits to the telescope, which is called calibration. And you have to hope that there's an orthogonality that allows you to take your data and say, that belongs to the sky and that belongs to the telescope. And we'll come on to this a bit later, but I spoke about Faraday rotation earlier. Where did the Faraday rotate? Well, where did polarization leakage happen? Where did my one polarization leak into the other? Was it because that's what the sky was doing? Was the sky actually looking like that? Or was my feed doing it? And there's no way of knowing the two apart from each other. So so this is an experiment. It'll do one measurement only, and after that it gets decommissioned. Then, of course, you have telescopes like CAT7, which was a prototype, which you use for learning, and again, it has a fairly limited life. And then you go on to things like Meerkat. So, and then another experiment, Hera, again in the Kourou site. You can see that that's not going to last forever. It's absolutely an experiment trying to beat the SKA to its own game, trying to look for the epoch of reionization using these dish antennas. It's use once, one use telescope. But if you want a Nobel Prize, that may be the way that you want to build your radio telescope. And of course, SKA low is a log periodic array. It's a log periodic to give it the bandwidth. It works from 50 to 350 megahertz. The epoch of reionization signal is in a very much narrower band than that. So this is where this compromise came. If you build a very wide bandwidth antenna like that, even if you've got the best people in the world designing it, there is always going to be a compromise. So I always have to tell Bernie Fanroff when we were in the early days of CAT and Meerkat, Maxwell's equations are absolute. You can't break Maxwell's equations. There's no magic. No, all you can do is you can take bits of metal and you can configure them in different ways, but you can't do magic. If you go to wide bandwidths, you have to compromise somewhere. And so, this is the element of SKA, which is going to be looking for the epoch of reionization with the understanding that it is slightly compromised because it's actually trying to do more than just that experiment. Not knocking it, it's just the reality that you have. And then, of course, you have the no, SK mid, where we've made no compromises, um, designed by the best people in the world. So I mentioned this in the last slide as well. Why do you have SK low and SK mid? Well, there is a natural break in around about 350 megahertz where you're dominated by the sky temperature at lower frequencies and not so much to the higher frequencies. And then also because your receptor size is going with wavelength. And so as you go to the lower frequencies, your bare dipoles are actually quite good in terms of receptors. You might say a dish is a dish. Well, during the SK era, SK pre-design era even, when there was still what I call the amateur phase, where there were just a bunch of us sitting around the table discussing what we'd like to build, there was an enormous amount of work going into how to build reflector antennas, both in terms of what the optics should look like and then how to build it, the manufacturing process that you go for. The Allen telescope array pushed for hydroforming of single-piece aluminium sheets. Others were going for composites. No, with Cat7 and the XDM before that, we looked at using composite materials on a mold and all sorts of things. And the Canadians were looking at composites as well for big dishes. And interestingly, after all of that, when we came around to building Meerkat and now the SKA, we reverted to steel and aluminium. So it shows that innovation doesn't always take you to a new place. Innovation may take you on a new path and you try out all sorts of things. But our system engineers, Thomas Crystal in particular, sort of emphasized to us, concept exploration. Go look out there, but don't get waylaid by false promises. Remember, Maxwell's equations are always going to keep you honest. And we were lucky there. The same thing with feeds. Feeds is a great area to work in because there's just so many things that you can tweak and do and whatever. And again, everyone said, well, we can build these amazingly wide bandwidth things and Again, we were fortunate and that we were led by people who understood electromagnetics and enough radio astronomy to say, don't be over enthusiastic with bandwidth, stick to simpler things with narrower bandwidth where your calibratability is much simpler. You've got to think of the whole life cycle of a telescope, end to end. Just perfecting one bit of it is not going to help. The whole system has to work. And that includes being able to make images at the end that you can actually calibrate this thing, and we'll get on to that. So of course, I was going to all these meetings, and I was very trendy at the time, and ASCAP telescope in Australia is and the Apatief telescope that was in the Netherlands that followed through with this, was to say, let's not just have single pixel feeds on our telescope because that limits us to one patch on the sky. Let's effectively make a camera, multi-pixel feeds. That'll allow us to cover very much more of the sky because we can do it. And I particular was taken in by this, and I had to be taken aside, literally taken behind the bicycle sheds by some system engineers and told that that wasn't the way to go. But we went quite a long way down the line. In fact, we went as far as building prototypes of phased array feeds. Dirk Baker designed this one, and Dirk took it to the test range in Pretoria to go and test it. And that was the beginning of telling us that these things were never going to be very calibratable. So we dropped those ones. So this is sort of a bit of introduction to the field of pictures. Now, inevitably, we have to end up back with some maths again. And this is where it gets a little bit eclectic. But this is just to sort of, you might hear these terms being spoken about, and hopefully it will give you something to pin onto. So some of you will know the Nyquist theorem in terms of sampling. So you take an analog signal, you digitize it, and you have to obey the Nyquist rate so you don't get aliasing. But there's another Nyquist theorem which tells you, which is a completely different thing, which says that if you've got a resistor, just a simple resistor, electronic circuit device, which is the simplest thing, and basically Ohm's law describes it, V equals IR, and that's it, it's a passive component. But it isn't if you're a radio astronomer. If you're a radio astronomer, it's a radio source. Resistors produce a voltage across their terminals just because they have a physical temperature. And you end up with the power that is produced by that resistor has a form which looks a little bit like the Planck equation we had earlier, and that's not surprising because it has the same roots. Um, the only difference is the Planck equation works in 3 dimensions, a resistor works in 1 dimension, and you end up with a very similar looking equation, which is, looks a bit nasty, but we make the same approximation. We say, well, we're not interested in high frequencies, we're only interested in the regime, low frequencies effectively, and if we do that, we end up with an equation that says the power produced by the power that can be extracted from a resistor is equal to Boltzmann's constant times its temperature. Now that is a very, very, very useful thing when you're a radio astronomer, because there is your absolute calibration. If you want to calibrate a noise source, this is your gold standard. You have a resistor and you measure its temperature, and that equation tells you how much power you're going to get out. Also, very conveniently, because of Boltzmann's constant being in there, it's a very, very, very small power as well. So you can use it to calibrate your radio telescope. Now, just like we did with brightness temperature, we can say, oh, that's nice. No, that's a, no, we can measure, we can say how much power is going to come out of a resistor. Let's turn that around and say, let's define a thing called noise temperature to be the power in a signal and divide it by Boltzmann's constant and its bandwidth. And that will end up as what we call a noise temperature in kelvins. So when you hear about noise temperatures in kelvins, remember what that actually is power. So it's just radio astronomy speak for power. So radio astronomy speak for intensity is kelvins. Radio astronomy speak for power is kelvins. The two, and this is where you can see there's some convenience that might come out of this. So it's used in the place of power spectral density. You can see it's power per unit bandwidth. And it's also used to define what I'll see just now is called an antenna temperature. So if you have an antenna, conceptually you think of having an antenna, reflector, whatever, and a feed, and there's 2 wires that come out of it, an X polarization and a Y polarization wire. And if you measure the power at those terminals, we call that the terminal power, and we convert that power into an antenna temperature. So we say that the antenna temperature is so much, that's the power that we would receive at the terminals of our antenna. It's just converted to a temperature, just to confuse people. So let's move on now to now we're going to be dealing almost certainly only with reflector antennas. So this is a simple sort of one-dimensional view of a center-fed reflector. So we have a primary reflector, which normally would be a parabola. These days we shape these things so they're not just pure conic surfaces, but if you have a parabola, it's got a focus, and you go and stick your feed at that focus. And the feed, we confusingly use transmission terms quite often. So we say that the feed illuminates the dish. It's actually the other way around. The dish illuminates the feed. But because we think of the feed as having a transmission pattern, we say that the feed illuminates the dish. Now, reciprocity says that it doesn't matter which way the radio waves go through this thing. We can reverse time effectively. So we can use transmission and reception interchangeably. So it's very convenient. You can swap between the two whenever you want to. But what that means is that if you take a cross section across that aperture, across the reflector, it means that the feed will sort of have a more intense illumination of the center of the dish than the edges of the dish, because that feed will have a pattern which falls off sort of from the axis of the feed. So you get an illumination of the dish which falls off towards the edges of the dish. Yeah.
Sorry for the people that was Adrian sticking up his hand again. I just want to know, is this feed pattern linear or the same across all frequencies, or
No.
is it? Okay.
No, I mean, that's one of the issues, is it does change with frequencies. But if you go to a very good antennas company down the road in Stellenbosch, they will build you one which just gives you a pretty constant pattern across frequency. But again, and that's why you go for the narrowband feed, because the narrowband feed, you can do that. Wideband feed, you can't hope to be constant across frequencies. So you try to do that, but no, so you end up with an aperture illumination function, but there's a big hole in the middle because you have to stick the feed in the middle. And then you have to support the feed on legs. And so in fact, if you look at this in 2 dimensions, that aperture is blocked in many ways. But you end up with this concept of an aperture plane, which is the sort of the defined by the main reflector, and an illumination function, which is sort of peaked in the middle and falls off towards the edges. And we speak about edge tapers and whatnot. Then you go to your classical optics book. Bourne and Wolf is the one that we used to use to teach these things. And basically, if you a reflector, well, any antenna, but a reflector antenna in particular, is an exercise in diffraction. So as I was saying earlier, no, we sort of talk about reception and transmission in equal terms. What you can think of as the circular aperture of a radio telescope, you can think of it as a hole in a big sheet of metal, and then you illuminate from behind that hole, and you get a diffraction pattern looking forwards. That plays backwards. If you're receiving radiation into that aperture, then that diffraction pattern that you saw earlier is the directivity, or it's the gain that you get for signals coming in to the antenna. So you know, those of you who know diffraction, you normally get these fancy sort of sync type function things and with side lobes and whatnot. The bottom line is what that all means is that you go to your physics textbook on diffraction, and you look under Fraunhofer diffraction, and Fraunhofer diffraction defines the relationship between the aperture illumination function and the beam on the sky. That's either the transmission beam or the reception beam. They're both the same. So now we move to 2 dimensions. So you've got 2 planes. You've got the aperture plane over there. We scale that into coordinates of u and v, where u and v are x and y scaled by wavelength. And then in the far field, which we can do in astronomy because all of our things are a long way away, far field basically means that r squared over lambda is very much greater than 1. You end up with a beam, and the coordinate system we use there is L and M, which are direction cosides. But there's Fraunhofer diffraction is a approximation, but a pretty good approximation, says that there's a Fourier transform relationship between those 2 things. And so now you've got this tool in your head that when you see an aperture illumination function, you can get some sort of idea about what your beam's going to look like. Now, this is a one-dimensional cut through things, but you know that if you take a Fourier transform, the 2-dimensional Fourier transform of something like that, you're going to get a mess in the sky because you've got all sorts of sharp edges and whatnot. And when you take the Fourier transform of those sharp edges, you're going to end up with side lobes. Your antenna is not going to be looking where you want it to do, straight ahead. I've got some pictures for this, I hope, just now. Okay, sorry about this, maths, but this is just to give some definitions. The antenna will have a physical aperture. You go out there with your tape measure, you measure the dimension or the projected dimensions of the dish, you use pi r squared, that gives you the physical aperture. The effective aperture is always going to be smaller than that. Because of the aperture illumination function falls off towards the edges, the dish is never going to be 100% efficient. In fact, it's kind of hard to get it up to 90% efficient. But if you go to clever people at Stellenbosch University, they will find ways of shaping your dish and optics that you can get up towards 90% and above. So the effective aperture is, how big a size does this thing actually look like? So if you think of the antenna as a rain collector, now how much rain am I going to collect on this aperture if I measure how much water I've got out? How can I convert that to millimeters of rain? And you can see that it's got a complicated integral function of the aperture illumination function. We then have what we call the power beam. That's the beam in the sky, which is basically the square of the voltage beam, and it's normalized so that it's normalized to 1 when we're looking directly along the bore site of the antenna. But we'll see some pictures of this just now, which makes it easier to see. But and then we define the aperture, the beam solid angle as a 2-dimensional integral of that. It doesn't all matter either. But there's a fundamental equation that comes out of all of this when you do the analysis, that AE, the effective aperture, times by the beam solid angle. Beam solid angle is a measure of the size of the beam, how broad the beam is. The product of those 2 is equal to lambda squared. And before you ask the question, it's dependent on lambda, so it's going to change over frequency. Anyway, so those are just the terms that you might hear, and you can come back to this. So these are some pictures which kind of attempt to show that. So there we see what this beam looks like. It's a sort of, it's looks like a, looks like a truncheon. But you've got this main beam in the middle, which is, where you're going to get most of your signal from, which is hopefully perpendicular to the antenna. It falls off as you move away from the center, but then there's side lobes. And those side lobes come about because this thing is the Fourier transform of the aperture illumination function. The aperture illumination function had sharp edges. Fourier transforms of sharp edges give you ripply things that come out into the outside. Side lobes are bad. You'll see why that is just now. So you take your telescope, you point it up at the sky. We saw in the previous lecture that we look at intensities in the sky. So we're looking for the intensities, and we convert those intensities into brightness temperatures, TB. We then, having pointed our telescope at the sky, we look at the terminals of the antenna, and we measure the power that's coming out there. And we convert that into an antenna temperature, TA. So we take that power that we receive, PRX, divided by Boltzmann's constant to the bandwidth. Then we say, how are the intensities in the sky and the powers that we receive out of our antenna related? It's what looks like a complicated integral function there, but basically the power we get out is a half. Now, why the half? This is an odd thing because we only detect one polarization per feed direction. Half the power is assumed to be in one polarization and half in the other, hence the half. Then the power is proportional to the effective aperture. That's kind of obvious. The bigger the antenna is, the more power we're going to get. And that's why we build big antennas to do that. And then it's the integral of the beam in the sky multiplied by the intensity in the sky. So like a weighted average of the sky, and multiplied by bandwidth. Now, this is why it's nice to use temperatures instead of powers and intensities, because when we substitute the powers and the intensities with temperatures, the bandwidth disappears, and what you get, and you use the little identity we had earlier about AE times omega A equals lambda squared. What you end up getting out in the end is that the antenna temperature is 1 over omega A, which is the beam solid angle, multiplied by that integral. So what we get out of a single dish radio telescope is not a power that's determined by a single point in the sky. It's integrated over the area of the sky that the beam of the antenna is looking at. So if you have a narrow beam, you're looking at a fairly small bit of the sky. If you've got a big beam, looking at a big piece of the sky. And that's why radio telescopes, traditional single dish radio telescopes, have got really bad resolution. The size of the beam is approximately lambda over d, the wavelength divided by the diameter. And that means that normally your beams are of the order of a degree. So the Meerkat single dish beam at L band is about a degree. So that's bigger than the moon. So you can't make pictures of the moon because you point at the moon and you're looking at the whole moon, not just a single point on the moon. But still, even in arrays, this all works. So this is basic sort of radiometry. What do we see when we point our telescope looking up at the sky? And it's all in terms of power. So we now take that antenna voltage and we put it through these cryogenic receivers. Why cryogenic? Well, we saw earlier that even a resistor gives off power, noise power, because of its physical temperature. Radio receivers have resistors and other electronic components. They'll be giving off their own noise. The way to get rid of that noise, or not get rid of it, but to reduce it, is to cool those components down. And that's why we spend lots of money on cooling these things down. Now, one of the things that our system engineers were really good at in the Meerkat days was to look at the system. And so people were saying, oh, cryogenic receivers are very expensive. Helium coolers, that sort of stuff, very expensive. We're not going to go that way with the SKA because it doesn't work. But we'll see just now that there's some important metrics, a sensitivity metric for a telescope. What you've got to do is you've got to take the system performance, put a cost to each of those things, and say, how do I get the best bang per buck? So even though it might look like helium cooling systems for telescopes are very expensive, it's a lot cheaper than building a bigger telescope. And so that cost-benefit analysis needed to be done. So these are very complex beasts. I mean, you're having to cool these things, the receivers, down to less than 20 Kelvin absolute. They have to be in a cryogenic vacuum flask, effectively, to stop heat transmitting through the system, coming in. And but to say, fortunately, we have some very good people who can do this for us. So this is the sort of mathematical reasoning for all of this. So from the picture I showed earlier of what a radio telescope looks like, it's a cascaded system of things. You have blocks going through. So what I've sort of tried to represent here is basically a radio telescope receiver. So that where the T in over there is the antenna temperature. That's what you've connected to the terminals of your antenna. But that bit of stuff that you have there may actually have some loss. Now, physical systems always have loss. There's a resistive loss in things. So you may have something which is lossy up front, and then you have gain. Then you want to get that signal boosted as much as you can. And so you put a whole lot of gain blocks in. Now, each of those units in there will have an intrinsic what's called noise temperature. And it depends on the design of the thing or whatever. And it's got a gain. So the way that you characterize an amplifier is to give it its gain and its noise temperature. How much noise does it add into the system? And if you string things together like that, then you can say, well, if I treat that whole thing as one block, what is its noise temperature? And the equation for that is Free's formula at the top there. And what you see is that you just take each of the elements as you go from the front to the back, and you add those terms together. You take the noise temperature of the first one, and you take the noise temperature of the second one and divide it by the gain of the first one. Now, the name of the game is to make that noise temperature as small as possible. So how do you do that? Well, you choose the T's to be small, because that will first off give you a good thing, and you make the G's big. And you also arrange these things that if they've got big T's, they're further down to the right because they get divided through by the previous G's. Now, if you do that for the specific case that I've got here, and not just have G's but L's as well, have a lossy component. Now, the lossy component in say Meerkat is the what we call the OMT, the ortho mode transducer. It is the thing that converts the radio waves into voltages, and it's bits of metal, and they're big bits of metal, and they may even be gold plated and whatnot, but they still have a loss, and because they have a loss, you can come up with an equation that says that the noise temperature of a lossy device is equal to the loss minus 1 times its physical temperature. So what do you do to keep that low? You make sure the loss is as low as possible, but you also lower the temperature of the OMT. And that's what we've done in Meerkat, is we lower the temperature of the OMT as well. Because then what you end up with Free's formula, it looks like, I've got at the bottom there. So your noise temperature can be dominated by any loss that you've got at the front. Now, all of these enthusiastic feed designs that came out in the early SK era all had huge losses. And you can't overcome that loss because it's not divided through by any of the next gains. Putting more gain behind a loss doesn't buy you anything. Logic, very easy logic, but and this is one of the key things in radio astronomy. This is how you build good radio telescopes, is you use Free's formula to do a noise budget for it. So this is very eclectic. How do you measure, so in radiometry, how do you measure a signal power? These are very small signal powers that we're looking for. How do you measure them? And you'll often hear, especially during commissioning, you'll hear about Y factors and things like that. And what you do is you make an assumption that the whole system is linear. And so if you look at the output power from your system, what it's going to be is it's going to be the sum of two components. It's going to be the signal that you're putting in plus the noise contributed by the system. So the noise put in by the system is some sort of constant, you hope. And then you've got a linear system. So if you put in more power, you get more power out. So you end up with a simple, school, graph of input power versus output power. So if you've got a device under test and you put various signal powers into it and you measure the output powers, all you've got to do is you characterize that straight line. And if it's a straight line, you only need 2 points to define it. And we talk about hot and cold signals. We put a cold signal in and a hot signal in. Those 2 points, we measure the output powers, and those powers can be arbitrary units. We don't have to know what those powers were. We can then fit that straight line, and the x-intercept turns out to be minus the noise temperature of that component. So this is how we measure the noise temperature of our receivers. Having built them, we predict what we hope to get, but what you have to do is put in 2 temperatures. How do you put those temperatures in? Our resistors. We've got resistors at 2 different temperatures, which give us absolute powers. So it's a very simple way, and the Y factor is the ratio of the hot output divided by the cold output, and given the Y factor and knowing the temperatures of your two loads, you can end up with characterizing the noise temperature of your system. And the implementation of this is done in various ways. You can do it in the lab, or you can do it in the sky. What you can do is you can point your telescope at the moon and then point it next to the moon. The moon is at about 200 Kelvin. Next to the moon is about 10 Kelvin. And so you've got two input temperatures to your telescope, measure the Y factor, and you get the system temperature of your telescope out of that. And during commissioning, people are going to be doing such things. So been talking about the system temperature. What the system temperature is basically, what is the power, total power that comes out the back of my telescope. And it's got, at the high level, it's kind of got three components. There's the antenna temperature, so what's coming in from the sky. There may be a noise diode. A noise diode is a calibration device that we can turn on and off. It's a calibration signal that we stick in. And then there's the receiver temperature. So what is the noise temperature of our receiver? You can split these things up further as you go along. How do you get the antenna temperature? That consists of two components. One is our sky signal, the one we want from the astronomy sources. The other bit is from the Earth, from the ground, terrestrial, which is really bad. And then but we can split the astro signal up further. We can say the astro signal, okay, we said it's always going to be the cosmic microwave background. There's going to be all these extragalactic AGNs and other radio sources that we know about. There's our own galaxy. We may be looking at the moon or the Jupiter. And by the way, looking at our source as well. So the thing, remember, what we want here is our source. What's coming from the ground is the Earth's atmosphere, gives us radiation. There's spillover from the ground. The ground is 300 Kelvin. It's a hot, hot source. And it scatters into the telescope, especially if you don't build it properly. And there's RFI, which also adds in. And then the noise diode and the receptor. So when you look at that, and especially as the total power person that I was back in the day, the signal you're looking for is a needle in a haystack. T-source is only one of many components, many of which are far bigger than the signal that you're looking for. So at this point, you say, why do you become a radio astronomer? Because what you do is you say, absolute measurements are almost impossible. I'll do relative measurements. And so you do two measurements, where the only difference is that in one measurement, you're looking at the source, and in the other one, you're not. And you take the difference between the two, and you subtract out all of those other things. But of course, you have to assume that they're remaining constant. And of course, they don't. And that's why it takes 15 years to do a PhD. If you do, it takes you 1 year an interferometer, it takes you 15 years at Hartepiers Hook. So that's another story. But then a really central equation to radio astronomy. So this is very eclectic stuff, but no, hopefully, if you need to know about this, you can look back at this. The radiometry equation. So the absolute system temperature is basically an average power that you're receiving. That's not the big problem. The big problem is that power fluctuates just because of statistics. And so if that was completely constant, that'd be fine. You just have a constant you can subtract out. But it's a constant with a variation on it. It's got a RMS variation on it. And that RMS variation is equal to the system temperature divided by the bandwidth of the signal and the integration time. So remember, in order to get your T-sys, you went through the square law detector. The square law detector had in the analog case, had a capacitor in it and a resistor, and that resistor and capacitor effectively averaged the signal. In the digital route, you had a digital integrator where you added numbers together, quite literally. And so if you want to get a smaller RMS value, that fluctuation, because that fluctuation is the noise in your signal, the actual noise, you have to have wide bandwidths and long integration times, both of which cost you money. The one is a technology issue. The other one is just you have to run the telescope for longer. And maybe your source doesn't allow you to do that. So from that, you get some really important metrics out of all of that. So I've already said that the system temperature is the sum of a whole lot of things, most of which you don't have any control over. You can't make the galaxy go away. You can't make the microwave background go away. But through good design, you can make sure that the spillover temperature of your antenna. In other words, its reception towards the ground, the beam towards the ground is minimal, and you build a receiver temperature, which is, no, you build a receiver with low temperature. And that's what you need to, the atmosphere you can maybe get rid of or mitigate by building at higher altitudes, and that just costs a lot of money and doesn't make any sense when you're working at Meerkat and SKA wavelengths. There's a metric that's used which compares looks at what it's called the system equivalent flux density. It says, if I compare my system to a radio source in the sky, what is its flux? And you get this thing, 2K times 10 to the 26 over AE over T-cis, but it's the AE over T-cis that's important. You want this SEFD to be as small as possible. That means you want AE over T-cis to be as big as possible. AE is the aperture, T-cis is the system temperature. That was the design equation that we used for building Meerkat and the SKA subsequently. Getting as much effective aperture as you can, lower the system temperature as much as you can. All of that work, that optimization work, was done by South Africans. One of which was a product of the Human Capital Development Program and is now a research chair at Stellenbosch. You build an optical system which maximizes AE, and you lower T-cis by building a cooled receiver. The AE side of things is basically numerical calculations to make sure that you've actually, it doesn't cost any more to up AE. Once you've got a fixed aperture, you just have to get the right shape. You have to, and then design your optics to give you the best AE. The illumination of that dish has to be optimized. And then you get the best A over E. And there's good reason for doing that, because one of the reasons that this is a useful metric is that the amount of time that you need to spend observing a source to get to a certain sensitivity goes as the square of A over T. Now, you say, well, so what? Well, the biggest cost of a radio telescope is not building it, it's operating it. R1,000,000 a day for Meerkat. If your observation takes twice as long, if you have half the A over T, it takes you 4 times as long to do your experiment. 4 million rand against 1 million rand. So no, but that's why thinking of the thing in the entire life cycle of the system is important when you're designing a radio telescope. I doubt that many of us will be designing many more radio telescopes into the future. The SKA will suck up everything, but that's what we had, the thing that you need to take into account. I'm now treading in territory which is very, very dangerous, because there are certainly people in this room who know more about this than me. And this is about calibrating, starting to think about how to calibrate. Now, not just a single dish anymore, but an interferometer. It's much I won't say it's much easier. It's more possible to calibrate an interferometer than a single dish, because you've got multiple dishes and you can do this magic correlation stuff. So the basic job of a radio telescope, certainly the dish part of it, the antenna part of it, is to convert the E field coming in, the electromagnetic E fields coming in 2 polarizations. And we work in linear polarization, we can equivalently work in circular, but because Meerkat and the SKA are both linear receivers, you've got an X polarization and a Y polarization coming into from the sky. And when I say from the sky, you have to think about, say, above the Earth's atmosphere, because all of the interfering effects, all of the distortion effects happen from above the atmosphere and come down. So that's what you've got up there. And then you measure antenna voltages coming out of your antenna. You've got an X plane and a Y plane dipole, which pulls those 2 things out. And this is the Jones formalism for describing these things. Now, all of these quantities here are complex valued. They're not real numbers, they're complex numbers. And this is, you have to sort of get your head around this, because you can say, how can the E fields be complex? They're not, they're real. They're real numbers. You measure an E field in volts. Volts is a real thing. But in order to do the maths more simply, you think about them as being analytic signals. And analytic signals are complex signals, where you take the real part of you take the signal, the real signal, you apply a Hilbert transformation to it, and then you make that the complex part, the imaginary part of the signal. So there's no new information. All you've done is you've taken your signal and you've made it into a complex signal. So in the electronics courses, the elementary electronics courses, they talk about phasors, not phasors, but phasors. So what you say, if you have a cosine signal, cos omega t, that's the real signal, then the analytic signal, or the phasor, is cos plus j sine omega t, because sine is the Hilbert transform of cos. So there's no new information. You've just added it in. And the nice thing about it is that the argument, the phase of that complex number is the instantaneous phase of the signal, which you can't get from just the real signal. If you've just got the instantaneous value of a real signal, you don't know what its phase is. You need to know what's happened on either side. But an analytic signal, you know the phase at any one time. So you want to, so no, it's a conceptual thing in a way. So, but all of those numbers are complex numbers, and the Jones matrix with its J terms there are, you assume this whole thing is linear. So what you see is that Vx, the voltage you get out of the X polarization, is some complex number times by Ex, that's great, that's pretty good, but also plus some complex number times Ey. There's polarization leakage. One polarization is getting into the other. You don't want it, but it's going to happen to you, and you have to deal with it. And so that's the base, well, the sort of the starting point for understanding how we call the measurement equation, how the sky signal is related to what we see down here in our telescope. So what we want, the whole thing about calibration is that we measure something through this measurement equation. We have to go back. We measure this, but we want the sky. So we have to invert that equation. That means that Jones matrix has to be inverted. And if you know about linear algebra, you know that square matrices can be very badly behaved if they're not well behaved, which basically means you want them to be diagonal and all sorts of other things. So you want the Jones matrices to be good. Well, one of the Jones matrices that we'll see, I think in the next lecture, the Jones matrix that is associated with the antenna optics, which is the beam. You want the beam to be really nice because it makes it easier for you to do the calibration. Now, I've already said, if you have a center-fed dish, like the top one over there, center-fed symmetric dish, like Cat7, there's a lot of blockage, which means that your beam is horrible. But if you go for the more complex offset Cassegrain dish, then you don't have blockage, and you end up with a much nicer beam. This is, again, where the system sort of level thing comes in. It costs more, but actually it adds to the bang per buck. And this is the picture which shows beams. So the left-hand beams there, that's the Cat7 beam, and the right-hand beam is the Meerkat beam. And you can see that that left-hand beam is a mess. The right-hand beam is very much nicer. And not the least of which, because each of those side lobes is receiving signals, and means we're seeing a lot more satellite signals than you would do with the Meerkat beam. So the beam is one of the Jones matrices. In order to do this design, these days we have the mathematical, the computational tools to do this. Not only does it allow you to design your beam, sort of up front, but it also then allows you to analyze your beam afterwards to say, how well does my optic actually achieve what we built? And so, we use interferometry, we use holography to measure the beam afterwards to say, how does it match up with our simulations before? We're doing that for now, well, say we, the Royal We, Mathieu de Villiers is doing that for the Meerkat extension dishes as we speak. Yeah, so there's our dish with its receivers and everything else on it. Says it's very eclectic. Radio telescopes have very esoteric and less esoteric bits. One of the less esoteric bits are the control systems. And so if you want to be the complete radio astronomer, you need to understand how PLC systems work. You need to understand control systems, that sort of thing. How do you tune a control system? And you actually have to get involved with what one of my colleagues calls red and black wires. Now, it's not all just electromagnetics. With waveguides and things, every now and then you have to get into things which have lots of wires in them. And so that's a sort of a skill that we have to do. Just going back to parochially again, so the little dish at Rhodes, a 22 gigahertz dish, it had the entire control system in there. And Graham Obram, who built this based on a very old computer, taught taught us control systems. So he taught himself control systems building a radio telescope, and then he went on to teach us how to understand the control systems. These the old days of computers with flashing lights and switches on the front were fantastic. It's also where I learned assembler programming. So now we've got these fancy digital dishes, digital telescopes, and this is a very conceptual idea of what Meerkat does. You have your antenna, you've got the analog signal conditioning, minimal, because you want to do as little analog as you can. Go to the ADC, have a digital system, maybe do digital down conversion, and we do that with Meerkat in the L band, where you get down conversion for free because of the magic of Nyquist zones. And we'll get back to this in the next talk. You have to put in a delay because you've got an array of antennas, and the radio waves coming in from a certain direction. There's going to be different geometrical delays to the different dishes depending where they are. You have to back that out. And then, very importantly, you have to channelize the signal. You've got a fairly wide bandwidth signal, and the first thing you want to do is to get that into narrow frequency channels. And this is what we can do these days with modern radio telescopes. We've got the hardware to do it. And we saw in the previous lecture, one reason for doing that is that if you're looking at pulsars, they're dispersed. And if you look at the whole wide bandwidth, you're not going to see the pulsar. But you've got a half a chance of seeing the pulsar in each of these narrow channels. And especially if you know the dispersion, you can pile them all up, and Sarah will answer all the questions around that. Also, the great thing about the filter bank, no, if I got it in here, is, as I said earlier, we need an analytic signal. Now, everything that's happening in the first bit of this here is dealing with real signals. We get real voltages coming out of our antenna. The ADC doesn't do anything magic. The ADC just gives you samples coming out at real, of the voltage. The down conversion, digital down conversion doesn't do anything. But as soon as you go into the polyphase filter bank, you're taking a Fourier transform, and the Fourier transform automatically does the Hilbert transform for you. It's magic. And what comes out is a complex number. So you're at the right place now. You have got your complex analytic signal, which can then go into the correlator and beamformer. In the old days, before Fourier transforms and things, and FX correlators, we used to have XF correlators, they used to have real correlators. This is called a complex correlator. The Cambridge correlators and everything from before were real correlators. They did the correlation, but they did the Hilbert transform by doing a 90-degree phase shift using basically a RC network. That though only worked for very narrow bandwidth signals. And so today's complex correlators are actually more simple than the old days real correlators, because you were able to implement the actual mathematics that you wanted to do, which was complex correlation. Just on the digitized side of things, that work was all done here in-house, and you get tremendous amounts of data out of these things. Again, the time and frequency reference, really, really important part of the whole system. Rainier and others, have done fantastic work on this. It's not just having the local, time and frequency reference. You have to then, make sure that it's locked into the international system through GNSS Common View with Paris and other observatories. A really important thing. And in the next weeks or so, these two masers, which are our primary frequency sources, will be joined by the SKA maser plonked in here next to it. So that's a progress. The correlator, as we've all know, the Scarab correlator, which does all the magic for us. And what the correlator does then, so we're in the modern variety, the FX variety. We take the real signals, we put them through a PFB. Now, the polyphase filter bank, for those of you who know about IQ mixers, is basically a bunch of IQ mixers. And the output of an IQ mixer is an analytic signal. It's the I, which is the in phase, and the quadrature signals. And the quadrature signal is the Hilbert transform of the in phase signal. And so you get all of these complex signals coming out. So the V's that we get are complex numbers. And what the correlator does is it does that equation at the bottom there for all permutations of all voltages. So out of each antenna, we're getting 2 voltages, one for each polarization. Then what the correlator does is it takes all pairs of antennas and correlates all pairs of those voltages, including the same antenna. So the autocorrelations are where you take the signals from the same antenna and you apply them to each other. And you do that outer product that's that I show there. And you basically take the signals and multiply them by each other. They're complex numbers. Remember, you're multiplying two complex numbers by each other. Well, one complex number by the other one's complex conjugate. And you integrate over a time, and then you get a number that comes out, which is a complex number. And that's called the visibility, and that's the talk. That's the bit for the next talk.